Jntuk. Today we are going to explain the capacitance of a three-phase overhead lines. Okay. First, in the previous case, we derived the capacitance of a single-phase overhead system or the transmission system. In that, we are having the one single example is there. First, find out the capacitance of a single-phase line 30 kilometers long, consisting of a two parallel wires. Okay, we are having the single-phase transmission line and two parallel wires. Okay, each 15 mm diameter and 15 meters apart. Okay, the diameter is the 15 mm and the distance between these two parallel conductors are the 1.5 meters. Okay, the distance between the parallel conductors are the 1.5 meters. Okay, the radius of each conductor is the 15 meters by 2. Okay, then 7.5 mm is the radius. Okay, next the spacing between or the distance between the parallel conductors, that is D. Okay, the distance between the parallel conductors is the 1.5 meters. Okay, the distance between the parallel conductors is the 1.5 meters. That is equal to 1500 mm. Okay, that is equal to 1500 mm. Okay, next we calculate the capacitance of a single phase overhead transmission line. Okay, this is the given problem. In that we are having the diameter and the radius. Okay, diameter and the distance. Okay, then we calculate the capacitance of a single phase overhead line. Okay, the single phase overhead transmission line, when the two parallel conductors are there, therefore the formula for that, the capacitance value, that is the C is equal to the pi epsilon naught log E d by R, okay, into length of the line. Okay, into length of the line. Okay, this is the capacitance of a line in the case of a single phase overhead transmission line when the two conductors are connected in the parallel. Okay, when the two conductors are connected in the parallel. Okay, therefore substitute this epsilon naught is the constant value, that is 8.854 into 10 power minus 12. Okay, by log E D. D is the spacing between the conductor and R is the radius of the conductor. Okay, what is that D? That is 1.5 meters, that is 1500 mm. Okay, that is 1500 mm. Okay, next D by R. Okay, R is also in the millimeters. Then we calculate the spacing between conductor is also in the mm. Okay, then 1500 by 7.5 into length of the line. Okay, what is the length of the line? That is 30 kilometers long. Okay, that means 30,000. Okay, the length of the transmission line is 30,000. Okay, this is the capacitance of a single phase overhead transmission line when the two conductors are connected in the parallel, and we give the diameter and radius and diameter, distance and the length of the transmission line. Okay, by using these values we determine the capacitance value, that is the 0.1575 microfarad. Okay, this is the capacitance of a single phase overhead line for the given problem. Okay, next coming to the what is the three phase capacitance of a overhead transmission line, and derive the expression for the three phase overhead capacitance. Okay, the capacitance of a three phase overhead lines. Okay, when we are calculating the three phase overhead line capacitance, we observe the two conditions, that is unsymmetrical spacing or the symmetrical spacing. Okay, when we are calculating the capacitance of a three phase overhead line, we observe the two conditions. Okay, that is unsymmetrical space line, second one is the symmetrical space line. Okay, first unsymmetrical space line. Okay, for an untransposed unsymmetrical three phase line, the capacitance between the conductor to the neutral of a three phase conductors are different. Okay, when we are taking the unsymmetrical spacing between the conductors, then the conductors to neutral of these three-phase conductors are different. Okay, suppose that the line is as shown in this given figure and the voltages are the VA, VB, VC. Okay, are applied to the conductors with the resultant that the charges per meter length are the Q1, Q2, Q3 respectively. Okay, the voltages are the VA, VB, VC, and also the charges are Q1, Q2, Q3. Okay, the potential of the conductor A with respect to the neutral infinity plane. Okay, the potential of the conductor A with a respect to neutral infinity plane. Okay, this is the unsymmetrical space of the line. Okay, in that first we calculate the, in the previous diagram, in the previous case we already derived the voltage for that A to N. Okay, therefore the potential difference between the conductor A to neutral point is the Q1 by 2 pi epsilon naught integral R to infinity. Okay, R is the radius of that conductor A. Okay, sir. Then dx by x, okay, plus q2 by 2 pi epsilon naught integral d1 to infinity. Okay, why we are taking d1, the A to conductor B is the distance between conductor A to conductor B is the d1. Okay, that's why we are representing the d1. Okay, d1 to infinity dx by x. Okay, plus Q3 by 2 pi epsilon naught integral D3 to infinity. Okay, the distance between the conductor A to B is the D3. Okay, then simplify this equation and then we apply the formula of that is integration, then 1 by x is the log x and then apply the limits, that is r to infinity, d1 to infinity, d3 to infinity. Okay, then we obtain 1 by 2 pi epsilon naught q1 log e infinity minus q1 log e r plus q2 log e infinity minus q2 log e d1 plus q3 log e infinity minus q3 log e d3. Okay, then simplify this equation and then q1 plus q2 plus q3 equal to 0. Okay, then substitute these values equal to the 0 in this equation, then we obtain 1 by 2 pi epsilon naught q1 log e 1 by r plus q2 log e 1 by d1 plus q3 log e 1 by d3. Okay, that is the VAN. Okay, that is the VAN. Okay, similarly VBN. Okay, therefore VBN is equal to 1 by 2 pi epsilon naught Q2 log E 1 by R plus Q1 log E 1 by D plus Q3 log E 1 by D2. Q3 log E 1 by D2. Okay, similarly we write down the VCN. Okay, 1 by Q3 log 1 by R. The radius of the conductor C is the R. Okay, the radius of the conductor B is the R. Okay, then D1 is the distance between the conductor A to B and D2 is the distance between the conductor B to C. Okay, then the radius of that conductor C is the R and the distance between the conductor A to C is the D3 and the distance between the conductor B to C is the D2. Okay, this is the formulas for that potential difference, the potential difference across the conductors, that is the VAN, VBN and also VCN. Okay, this is the final formulas that will be in the three-phase overhead transmission line. Okay, the capacitance of a three-phase overhead transmission line. Okay, this is the VAN and this is the VBN. Okay, and this is the VCN. Okay, this is the three formulas that will be related to the potential difference across the three conductors. Okay, then substitute Q3 equal to minus of Q1 plus Q2. Okay, Q3 equal to minus of Q1 plus Q2 in the above equation. Okay, above equation means the in equation number 4.38 and equation number 4.39. Okay, substitute Q3 equal to minus Q1 plus Q2. Okay, then we obtain VAN is equal to 1 by 2 pi epsilon naught Q1 log E D3 by R plus Q2 log E D3 by D1. Okay, D3 by D1. Okay, substitute Q3 equal to minus Q1 plus Q2. Okay, in VAN equation, then we obtain VAN is equal to 1 by 2 pi epsilon naught Q1 log E D3 by R plus Q2 log E D3 by D1. Okay, D3 by D1. Okay, next. VBN. Next, VBN is equal to the same. We will substitute Q3 equal to minus of Q1 plus Q2 in VBN equation. Okay, then we obtain 1 by 2 pi epsilon naught Q1 log E D2 by D1 plus Q2 log E D2 by R. Q2 log E D2 by R. Okay, then the equation number VAN by log E D2 by R. Okay, log E D2 by R and equation VBN by log E D3 by R. Okay, therefore VAN log E D2 by R. Therefore VAN log E D2 by R equal to 1 by 2 pi epsilon naught Q1 log E D3 by R into Q log E D2 by R plus Q2 log E D3 by D1 into log E D2 by R. Okay, log E D2 by R. Okay, next and VBM log E D3 by D1. Okay, then multiply the VBN equation with log E D3 by D1. D3 by D1. Okay, and left side and right side 1 by 2 pi epsilon naught Q1 log E D2 by D1 log E D3 by D1 plus Q2 log E D2 by R into log E D3 by D1. Log E D3 by D1. Okay, then subtract equation number 4.44. That means the VBN log E D3 by D1 with VAN log E D2 by R. Okay, then we obtain VAN log E D2 by R minus VBN log E D3 by D1. Okay, previously ఉన్న two equations ni మనం subtract చేస్తున్నాం. Then we obtain Q1 by 2 pi epsilon naught log E D3 by R log E D2 by R minus log E D2 by D1 log E D3 by D1. Okay, R Q1 is equal to the ఇక్కడ డివైడ్ చేస్తుంది కాబట్టి ఇటు వెళ్తే మల్టిప్లై చేస్తుంది 2 పై ఎప్సిలాన్ నాట్ ఇంటూ విఐఎన్ లాగ్ ఈ D2 by R మైనస్ విబిఎన్ లాగ్ ఎన్ D3 by D1 బై ఇక్కడ మల్టిప్లై కాబట్టి ఇక్కడ డివిజన్ బై లాగ్ ఈ D3 by R log E D2 by R minus log E D2 by D1 log E D3 by D1. Okay, log E D3 by D1. Okay, therefore the capacitance of a conductor A2 neutral. Okay, therefore the capacitance of a conductor A2 neutral CAN is equal to the Q1 by Vn. Okay, what is the formula for that capacitance? C is equal to Q by V, where Q is the charge in coulombs and V is the potential difference in volts. Okay, V is the potential difference in volts. Okay, therefore the capacitance CAN. Okay, therefore the capacitance CAN is equal to Q1 by VAN. Okay, what is the Q1? Q1 is equal to 2 pi epsilon naught VAN log E D2 by R minus VBN log E D3 by D1 by log E D3 by R log E D2 by R minus log E D2 by D1 log E D3 by D1. Okay, this is the Q by VAN. Okay, by VAN. Okay, by VAN. Okay, then similarly, we write down the equation for VBN and also VCN. How we will write down the equation for that VBN? VBN is equal to the, okay, therefore VBN is equal to the Q2 by, okay, Q2 by VBN. Okay, VBN. Similarly, CBN is equal to the Q2 by VBN. Okay, similarly, CCN is equal to the Q3 by VCN. CCN is equal to the Q3 by VCN. Q3 by VCN. Okay, that is the capacitance of a three-phase overhead transmission line for unsymmetrical spacing. Okay, that is the capacitance of a three-phase overhead transmission line for the unsymmetrical spacing. Okay, for an unsymmetrical transposed unsymmetrical conductors, the voltages are the VA, VB, VC, and the charges are Q1, Q2, Q3 respectively. Okay, in the previous derivation also we observed the capacitance value, that is, are we calculating the VAN. VAN is equal to the Q1 by 2 pi epsilon naught integral R to infinity dx by x plus Q2 by 2 pi epsilon naught integral d1 infinity to dx by dx. Okay, d1 is the distance between the conductor A to B, and plus Q3 by 2 pi epsilon naught integral d3 to infinity dx by x. Okay, where d3 is the distance between the conductor C to A. Okay, then we simplify this equation, then we obtain VAN is equal to 1 by 2 pi epsilon naught Q1 log E 1 by R. R is the radius of that conductor A, and Q2 log E 1 by D1 plus Q3 log E 1 by D3. Okay, similarly, we write down the equations for VBN and also VCN. Okay, similarly, we write down the equations for that VBN and also VCN. Okay, after that, we substitute the Q3 is equal to the minus of Q1 plus Q2. Okay, in equation VAN and also VBN and also VCN. Okay, then we obtain VAN is equal to the 1 by 2 pi epsilon naught Q1 log E D3 by R plus Q2 log E D3 by D1. Okay, then subtract VAN minus VBN or subtract VBN minus VCN. Okay, ఏదో ఒక ఈక్వేషన్ లో నుంచి ఒక ఈక్వేషన్ కానీ మనకి సబ్ట్రాక్ట్ చేస్తే then easily we write down the Q1 or Q2 or Q3. Okay, first we subtract the VAN minus VBN, then we obtain the Q1. Okay, next subtract VBN minus VCN. Okay, then we obtain Q2. Okay, then subtract VCN minus VAN. Okay, then we obtain the Q3. Okay, first we subtract VAN minus VBN, then we obtain the Q1 is equal to the 2 pi epsilon naught VAN log E D2 by R minus VAN log E D3 by D1 by log E D3 by R log E D2 by R minus log E D2 by D1 log E D3 by D1. Okay, this is the charge at a conductor A. Okay, then we obtain the capacitance. Okay, the formula for that capacitance is equal to the Q by V. Okay, therefore CAN is equal to Q1 by VAN. Okay, therefore CAN is equal to the Q1 by VAN. Okay, then that is equal to the 2 pi epsilon naught, that is equal to 2 pi epsilon naught log E D2 by R minus VBN by VAN log E D3 by D1 by log E D3 by R log E D2 by R minus log E D2 by D1 into log E D3 by D1. Okay, D3 by D1. Okay, similarly, we calculate the CBN also. Okay, then CBN is equal to the Q2 by VBN. Okay, CBN is equal to the Q2 by VBN. Okay, then we calculate the CCN also. Okay, therefore CCN is equal to the Q3 by VCN. Okay, Q3 by VCN. Okay, or otherwise we write down similarly the CBN is equal to 2 pi epsilon naught log E. Instead of D2 we are representing the D3 by R minus VBN means the VCN, VAN means the VBN. Log E, D3 is the D1, D1 is the D2. Okay, by log E, D3 is the D1 by R. Log E, D2 is replaced with the D3 by R minus log E. D2 is represented with the D3, D3 by D2 is D1 is represented with the D2 into log E. D1 is represented with D1, so D3 is represented with D1 and D1 is represented with D2. And similarly, we write down the CCN also. Instead of D3, we are taking as D1. Okay, VCN means the VAN by VCN. Log E, D1 is replaced with the D2, D2 is replaced with the D3. By log E, D1 is replaced with the D2 and D3 is replaced with the D1 and D3 is replaced with the D1 and also D1 is replaced with the D2, D2 is replaced with the D3. Okay, similarly that is the CAN, CBN and also CCN. Okay, we write down the equations for that next two also. Otherwise, we calculate the Q1 and after that we substitute Q1. So we calculate the Q2 by VBN. Okay, or CCN is equal to the Q3 by VCN. Okay, that is the capacitance of a conductor A, conductor B and conductor C for unsymmetrical spacings. Okay, for unsymmetrical spacings. Okay, next, the unsymmetrical lines with transposed conductors. Okay, we are taking the unsymmetrical lines and also the transposed conductors. Okay, assuming the charge per unit length is the same. Okay, assuming the charge per unit length is the same in each and every cycle. Okay, therefore the average voltage is equal to the VAN1 plus VAN2 plus VAN3 by 3. Okay, VAN1 plus VAN2 plus VAN3 by 3. Okay, this is the transposed conductors for unsymmetrical spacings. Okay, unsymmetrical spacing means that the distance between these three conductors are different. Okay, then by taking these transposed conductors, this is the distance between A to B is the D1 in first case and A to C is the D1 in second case and B to C is the D1 in third case. Okay, that is the transposed of the conductors. Okay, transposed means the ABC. First we are taking the ABC in the triangular form and second we are taking as the CAB and third we are taking as the BCA. Okay, BCA. Okay, this is the transposed of a conductors for unsymmetrical spacing. Okay, this is the transposed of a conductors for unsymmetrical spacing. Okay, the distance between the conductor A to B is the D1. Therefore, the distance between the conductor B to C is the D2. Okay, the distance between the conductor A to C is the D3. Okay, then the distance between A to C is the D1. The distance between A to B is the D2. And the distance between B to C is the D3. Okay, B to C is the D3. Okay, similarly, we are taking the another transposed conductor that is BCA. Okay. Therefore, the density of the charge on the either conductors will be partially unaffected by the charge. Okay, it is unaffected by the charge on the conductors. Okay, a uniform distributed charge on the conductor acts as it is concentrated on the conductors. Okay, it is concentrated on the conductors. Okay, and it having the plus q coulomb charge and other conductor having the minus q coulomb charge on the conductor B. Okay, plus q coulomb charge on the conductor A and minus q coulomb charge on the conductor B. Okay, these are concentrated at the centers of a two conductors. Okay, at the centers of a two conductors which are separated by a distance of d meters. Okay, which are separated by a distance of d meters. Okay, the conductor A having the charge of plus q coulombs and B having a charge of minus q coulombs. Okay, which are concentrated at a center of two conductors. Okay, these are concentrated at a center of two conductors, and these conductors are separated with a d meters distance. Okay, these conductors are separated with a d meters distance. Okay, we already known about the voltage of that conductor A in position 1. Okay, therefore VAN is equal to 1 by 2 pi epsilon naught Q1 log E 1 by R plus Q2 log E 1 by D1 plus Q3 log E 1 by D3. Okay, similarly, we are taking the VA2. Okay, VA2 is equal to 1 by 2 pi epsilon naught Q1 log E 1 by R. R is the radius of that conductor A. Okay, next Q2 log E 1 by D2. Okay, why we are taking the D2? In the second figure, the distance between the A to B conductor. Okay, VAN2. N2 means that this conductor potential difference. Okay, the distance between the conductor A to B is the D2. Okay, then we substitute, that is Q2 log E 1 by D2 plus Q3 log E 1 by D1. Okay, why we are taking the D1? D1 means that it is a distance between the conductor A to C. Okay, in the second diagram, what is the distance between conductor A to C? This is the A conductor and this is the C conductor. Okay, the distance between A to C conductor is the D1. Okay, distance between A to C conductor is the D1. Okay, then substitute, that is the D1. Okay, first in the first diagram, the distance between the B to A is the D1 and the distance between C to A is the D3. Okay, C to A is the D3. Okay, next similarly we write down the VAN3. VAN3 means the potential difference across the conductor A to neutral point. Okay, the potential difference across the conductor A to neutral point. Okay, in that 1 by 2 pi epsilon naught Q1 log E 1 by R. Okay, R is the radius of that conductor A. Okay, R is the radius of that conductor A plus Q2 log E 1 by D3. Okay, what is the D3? D3 is the distance between the conductor B to A. Okay, D3 is the distance between the conductor B to A. Okay, plus Q3 log E 1 by D2. Okay, where D2 is the distance between the conductor C to A. Okay, the distance between the conductor C to A is the D2. Okay, that is the formulas for that VAN1, VAN2 and also VAN3. Okay, next average these all the voltages are the potential differences of that conductor A. Okay, therefore VAN is equal to the VAN1 plus VAN2 plus VAN3 by 3. Okay, therefore by averaging these voltages, okay, then we obtain, that is 1 by 6 pi epsilon naught. Okay, then we obtain that is 1 by 6 pi epsilon naught into q1 log e 1 by r cube plus q2 plus q3 log e 1 by d1 d2 d3. Okay, this is the average of that voltages of a conductor A. Therefore, VAN is equal to the VAN1 plus VAN2 plus VAN3 by 3. Okay, VAN3 by 3. Okay, next, substituting Q2 plus Q3 equal to minus Q1. Okay, substitute Q2 plus Q3 is equal to the minus Q1 in the previous equation. Okay, then we obtain VAN is equal to 1 by 6 pi epsilon naught into Q1 log E 1 by R cube minus log E 1 by D1, D2, D3. Okay, substitute Q1 plus Q2 is equal to minus Q1. Minus Q1. Okay, then simplify this equation. That will be written as that is cube root of D1, D2, D3. Okay, then that is equal to the q1 by 2 pi epsilon naught log e cube root of d1 d2 d3 by r. Okay, cube root of d1 d2 d3 by r. Okay, therefore VAN is equal to the q1 by 2 pi epsilon naught log e cube root of d1 d2 d3 by r volts. Okay, next, calculate the capacitance. Okay, next we calculate the capacitance value. Okay, that is CAN. Okay, that is CAN. Okay, what is the capacitance formula? That is Q by V. Okay, therefore CAN is equal to the Q1 by VAN. Okay, that is equal to Q1 by what is the VAN? Q1 by 2 pi epsilon naught log E cube root of D1 D2 D3 by R. Okay, then simplify this equation, that equal to 2 pi epsilon naught log E cube root of D1, D2, D3 by R farads per meters. Okay, that is the capacitance of a conductor A. That is the capacitance of a conductor A to the neutral point. Okay, then equilaterally spaced lines. Okay, then we are taking the equilaterally spaced lines. Okay, in the equilaterally spacing means the D1, D2, D3 equal to D. Okay, suppose we are taking the equal distances between the conductors. Okay, then A to B, that will be observed in the diagram. Okay, the equilateral spacing means the A to B is D, and okay, this is D, and the distance between B to C is also D, and the distance between A to C is also D. Okay, equilateral spacing and also transposed conductors means this is A to C also D, and this is also D, and this is also D. Okay, in the similar way, all the distances are equal to D. Okay, therefore, the distances between the three conductors are is equal to the equal distances. Okay, that means the symmetrical distances. Okay, then we write down the formula when the distances are equal to the D. Okay, then we write down the formula when the distances are equal to the D. Okay, therefore, in the equilateral spacing, for the equilateral spacing, D1 is equal to D2 is equal to D3 is equal to D. Okay, then CAN is equal to CBN is equal to CCN. Why we are taking equal? All the distances from A to B conductor, B to C conductor, and C to A is the D. Okay, then we equal the capacitances also. Then CAN is equal to CBN is equal to CCN is equal to the neutral CN. Okay, that is equal to the 2 pi epsilon naught by log E cubed root of D into D by R. Okay, that means the D cube. Then we cancel cube and the cubed root. Then we obtain log E D by R. Okay, D1, D2, D3 is equal to the D. Okay, then substitute D1, D2, D3 is equal to the D. Then it is the D cube. Okay, therefore we cancel the cube and cubed root of cubed root, then we obtain log E D by R. Okay, then we obtain log E D by R. Okay, that is equal to the 2 pi epsilon naught by log E D by R. Okay, 2 pi epsilon naught by log E D by R. Okay, this is the capacitance of a unsymmetrical spacings and also symmetrical spacings for three-phase overhead transmission lines. Okay, for three-phase overhead transmission lines. Okay, ఈ formulas ని మనం ఇలా questions లో problems అడిగినప్పుడు ఇవి గుర్తుపెట్టుకోవాలమ్మా. What is the capacitance of a single phase overhead line when the unsymmetrical spacings అన్నప్పుడు CAN is equal to the 2 pi epsilon naught by log E cubed root of D1, D2, D3 by R. Okay, suppose we are taking the symmetrical spacings in the question, then we obtain CAN is equal to 2 pi epsilon naught by log E D by R. Okay, 2 pi epsilon naught log E D by R for symmetrical spacing conductors. Okay, for symmetrical spacing conductors. Okay, normally first we calculate the charge Q. Okay, after that we calculate the VAN, that is the potential difference across the conductor A to neutral point. Okay, that is the single phase or the three phase lines. Okay, suppose we are taking the unsymmetrical conductors, means the we are calculating the VAN1, VAN2, VAN3. Sorry, then we average that all the three voltages. Okay, then we average that all the three voltages and then we obtain the VAN. Okay, after that we calculate the capacitance, that is the CAN. Okay, therefore CAN is equal to the Q1 by VAN. CAN is equal to the Q1 by VAN. Okay, similarly we write down the formula for that CBN and also CCN, CCN. Okay, CBN and also CCN. Okay, therefore CAN is equal to the 2 pi epsilon naught log E cubed root of D1, D2, D3 by R. Okay, when we are taking the symmetrical spacing, means that the D1, D2, D3 are taken as the D. Okay, then it is equal to the D cube. Okay, cubed root of D cube is cancelled. Then we obtain the log E D by R. Okay, therefore it is equal to the 2 pi epsilon naught by 2 pi epsilon naught by log E D by R. Okay, 2 pi epsilon naught by log E D by R. Okay, this is the capacitance of a equilateral spacing lines. Okay, similarly we calculate the capacitance for single phase overhead lines and also three phase overhead lines. Okay, in the three phase overhead lines we are having the two conditions, that is the unsymmetrical spacing lines and also symmetrical spacing lines. Okay, in the symmetrical unsymmetrical spacing lines we are also taking as a transposed conductors. Okay, we are already taken as the transposed conductors, that's why we are calculating the VAN, VAN2, VAN3. Okay, this is the transposed conductors diagrams. In that we are transpose of that conductor A, C, B. Okay, then the transposed of that conductors are the B, A, C and C, B, A. Okay, this is the unsymmetrical spacing between the conductors. Okay, this is the unsymmetrical spacings between the conductors. Okay, same by using these formulas, we calculate or we derive the capacitance of that line. Okay, in the case of three-phase system also, only we remember the formulas for various conditions. That is, what is the capacitance of a single-phase overhead line, and also what is the capacitance of a three-phase overhead line for unsymmetrical spacing, and what is the capacitance of a three-phase overhead line for symmetrical spacings, and also for transposed conductors. Okay, we remember the formula, that is the capacitance formula. Okay, then we easily simplify or we easily solve the various problems that will be related to the capacitances. Only we remember that formulas. Okay, we write down the various formulas in the last page of that notebook. Then we easily remember that formulas. By using that formulas only, we substitute the d and the r values. Only we substitute the d and the r values. Okay, the epsilon naught value is the constant, that is 8.854 into 10 power minus 12. Okay, and the remaining terms are the d and the r. Okay, d is the diameter distance. Okay, d is the distance and r is the radius. Okay, that radius is given by that radius